Welcome back. For the past year, junior developers have been treating AI coding benchmarks like a game of copy-paste. For the past year, this is how the industry has evaluated AI software engineers. A developer drops a complete task description into an LLM, the model spits out a file, and the output is scored based on a single pass-or-fail unit test. This approach relies on a massive engineering fallacy. In production, you almost never have perfect frozen specifications. Real-world software architecture is cooperative and iterative. By treating AI coding benchmarks like a static game of copy-paste, the industry has evaluated models on their ability to mimic syntax rather than their ability to build systems. Relying on one-shot code generation metrics fails to prepare models for the reality of enterprise software development. We are training models to write isolated blocks of text when production environments require the management of evolving complexity. Meta's AI research division recently addressed this disconnect. They introduced SWE-Together, a sandbox benchmark curated from over 11,000 real-world developer sessions. SWE-Together abandons the static, one-shot output model. Instead, it measures how coding agents handle interactive, multi-turn software sessions over long horizons. Under this new framework, an agent cannot rely on a one-time output. It must actively clarify goals and handle constraints. If a human intervenes to change requirements, a static pipeline fails. An interactive architecture absorbs the input, identifies conflicts, and cycles back to correct logic. Software development evaluation now prioritizes the orchestration of long-horizon intent over simple syntax generation. To understand why standard models struggle with these interactions, we have to look at what happens when a human asks for a mid-project modification. This is context drift. Legacy models treat modification requests as isolated prompts, generating immediate fixes without linking to the global state. The context window fills with redundant data until the model exhausts memory, erasing the architectural plan. The model might write technically correct syntax for that specific turn, but it has lost the global map of the project. An agent's coding ability is secondary to its underlying architecture. If it cannot support plan preservation, it fails in a production environment. To quantify this, SWE-Together replaces static tests with a reactive LLM user simulator that intervenes while the agent is working. The benchmark tracks a continuous cycle: intent prompt, code generation, simulator intervention, and iterative adjustment. Scoring is based on the entire trajectory, how effectively the agent navigates intervention and reaches the goal. This yields two metrics. First is intent coverage, which measures if the agent stayed on track across the whole project lifecycle, despite the interventions. Second is user correction, which quantifies the exact amount of manual steering a human or simulator had to provide to fix the agent's logic blunders. Success in a multi-turn environment is defined by minimizing human friction. The goal is a system that can steer itself with minimal external guidance. Claude Opus 4.8 currently leads the SWE-Together leaderboard, showing significant advantages in the user correction and intent coverage categories. Its performance is tied to a hybrid reasoning engine that runs an internal verification cycle before it commits to any code output. This cycle, called adaptive thinking, allows the model to differentiate between a local code edit and a change that alters the global architectural state. Using dynamic workflows, the model maps a global dependency tree before execution. It leverages a massive context window to spin up parallel sub-agents, testing logic to identify edge cases before the user sees code. Opus 4.8 thrives in multi-turn environments because it treats the repository as a stateful system, managing it globally rather than treating it as a text completion task to be finished. When requirements change midstream, a robust architecture adjusts gracefully. The logic shifts to accommodate the need constraint without breaking the existing foundation. Consider a mid-flight constraint. At turn 4 of a project, the simulator demands a database schema swap to use soft deletes. While traditional models struggle with the sudden shift in context, the Opus 4.8 architecture maintains the global plan in its memory. Because it has mapped the repository's dependencies, it identifies exactly which downstream files require updates to support the new schema. By anticipating these dependencies, the system reduces the number of user correction cycles by 40% compared to standard models. Preventing regressions during mid-flight changes demonstrates that the model is maintaining a global architectural state rather than just reacting to the latest prompt. It is a mistake to treat these workflows as abstract magic. Deep learning and neural networks are distinct subjects with specific mathematical requirements. Managing these dynamic flows involves significant execution costs, complex hidden layers, and precise scaling of the memory footprint. Successful long-horizon state management requires the model to route its reasoning through the context window with extreme efficiency. Understanding the data structures that power these state machines is what separates the engineer who can steer an autonomous system from a passenger who can only watch it run. To prepare for this shift, move away from building basic one-shot code scripts. Focus on designing robust API layers and mastering interactive state management. Use the open-source SWE-Together framework to audit your own code bases against implementation-agnostic standards. High-value opportunities in engineering now belong to the orchestrators, those who can collaborate with, govern, and steer autonomous systems.